So here we are once again, and I want to just reiterate, we have the slope of the secant line. This broken line right here is our secant line. Its slope is rise over run. We have cleaned up the denominator. Our difference in our x values, remember, were x plus h minus x, which just algebraically left us h. When we pick this point up and move it along the curve toward the point x, f of x, they're occupying almost the same address in the Cartesian plane. It's not exactly the same, it's just infinitely close. We have two unique points still, but we've taken the distance between those points to almost zero, and we can get really, really, really close to zero. So the slope of the tangent line is a model for instantaneous rate of change. Huge. Enormous idea. Anytime you are asked to find the slope of the tangent line, I want you to equate it in your mind always to the derivative. The derivative is the slope of the tangent line at some point. The slope of the tangent line is the derivative of the function. So clearly what I want in your mind is the average rate of change is equivalent to slope of the secant line. The instantaneous rate of change is equivalent to slope of the tangent line. This is the derivative. When you read the words slope of the tangent line, or you read the word derivative, what I want you to think of is that those two things equal each other. The slope of the tangent line is the derivative. The derivative is the slope of the tangent line. So if I ask you what's the derivative, the answer needs to be the slope of the tangent line. If I ask you what's the slope of the tangent line, the answer needs to be the derivative. The derivative gives us instantaneous rate of change. Here is the definition of the derivative. We are going to be using the definition of the derivative over the next couple of lessons, which is right here. The definition of the derivative is this limit, and we are going to be finding the derivative at a point on functions. So we're going to use the definition of the derivative to work a couple of example problems to give you an idea of what homework is going to look like tomorrow. The next couple of lessons are going to be fairly, not great, but fairly algebra intensive, and I'm doing that on purpose because I know we need algebra practice. But still, never forget that the definition of the derivative is this limit right here. You are responsible for knowing that. You are responsible for putting that down on a blank piece of paper with no help. If you were told to memorize a formula for, let's say, the quadratic formula, you just had to put it in between your ears, whatever that process looks like for you, whether it's flashcards, whether it's practicing writing it when you don't see it, whatever it is, you need to know the definition of the derivative. When I tell you you absolutely need to know something, that means you need to know it from today until next May when you're taking the BC exam. We are going to have questions where you are going to have to use the definition of the derivative to answer those questions. So this says use the definition of the derivative to obtain the following result. If we are given the function f of x equals negative 2x plus 3, then this notation means derivative. Prime notation is one of a couple of notations that we're going to be given. If we are given a function f of x and they ask for this function, f apostrophe parentheses x means derivative. So this says if f of x equals negative 2x plus 3, then the derivative of x for all x everywhere equals negative 2. So we are to use the definition of the derivative to prove that is a true statement. If this, then that. So here's the definition of the derivative. It has separate pieces in it that I'm going to need to fill out. F prime of x equals the limit as h approaches 0. We know how to evaluate limits now, so that's not strange for us. Everywhere that this function has an x, this function has an x plus h. So in the numerator, the first thing that I'm going to list is the function f of x that they gave me with a parentheses where it has an x. This is a good practice, especially because our functions are going to get more complicated than just a function like negative 2x plus 3. So everywhere that there is an x, I put an open parentheses. And I recognize that this function machine, is feeding that function x plus h. It allows me to distribute that negative 2 correctly. I'm not trying to do it in 2 steps so that I make an error. Never go through your calculus work so fast that you're going to make errors. Right? Step after step after step. Remember, the AP reader wants to see your process. Here's the first obvious step in the process of evaluating this limit. We said for any limit, the very first technique that we're going to try to solve it is we're going to use the substitution theorem. On the substitution theorem, everywhere that there is an h in this function, I'm writing 0. That's what I'm doing, is I'm substituting in 0 for h. Well, what about the x's? X is not going to 0. H is going to 0. As far as h is concerned, x is a constant, and it's treating it as such. Well, we have a problem. Uh-oh. We can't divide by 0. So this is always going to be a problem in the definition of the derivative. How are we ever going to evaluate even one derivative using the definition if we run into mathematical trouble every time? Well, remember this for any limit that you evaluate. When you run into mathematical trouble, there's your indication that you have to use another technique. We can't use substitution theorem to evaluate the definition of the derivative. It's never going to work for us, so we're not going to use it. What's giving us trouble in this limit? The h in the denominator is giving us trouble in this limit. How can I do something algebraically that will help me get rid of that h in the denominator? Well, the only thing that's going to help me get rid of that h in the denominator is if I can find an h multiplied by everything else in the numerator. I need to factor an h out of the numerator. Because when I do that, it's going to get rid of or take care of my division by 0 problem. So let's do that. Let's clean up the numerator, number 1, and hopefully we can factor out an h. So the first thing I'm going to do is I'm going to distribute that negative 2. So my numerator is negative 2x minus 2h plus 3. Now I'm going to distribute this negative through those brackets. I get a plus 2x and a minus 3. All of this is still over h. Let's give ourselves some more room here. So let's clean this up. I have a minus 2x and a plus 2x. That's helpful. I have a plus 3 and a minus 3. That's super helpful. This algebraically cleans up to negative 2h over h. That's fantastic because the result is negative 2. Let's look back up at our problem. This says if f of x is negative 2x plus 3, then f prime of x equals negative 2. Look where we wound up. That is f prime of x at every point in the plane. So let's go back to our intuitive understanding of what the derivative is. The derivative is the slope of the tangent line, and this is a linear function with slope negative 2. We absolutely should have found that the slope of that function everywhere, not just at a few values, but everywhere, should be negative 2. So even intuitively, this idea of the slope of the tangent line and the derivative makes sense. But what we just did is we backed it up using calculus. We backed it up using the definition of the derivative. So now we're going to do one more example. This is not a linear function. This is a quadratic function. This time, given f of x equals this function, we are to show that f prime of x, the derivative everywhere, for any particular input value, is 2x minus 8. And we're going to use the definition of the derivative to obtain that. So let's do that. F prime equals the limit as h approaches 0. You're going to see me use the same process that I used on the last example. Everywhere this function has an x, I'm writing an open parentheses. That's all I'm doing in this step. It accomplishes a couple of things for me. It makes sure that I get f of x plus h listed correctly in my numerator. Then minus, all I have to do is copy down f of x as it was given to me. All of that is over h. Now every open parentheses, an x plus h was fed to function f. So everything this function did with x, this function fed at x plus h.